Hi everyone, welcome back to ECE111 classes. So today we are going to discuss two theorems, so which are known as Thevenin theorem and Norton theorem. So to start with, as we have already discussed, any theorem would require two conditions. First one is it should be linear, and second condition is it should be bilateral. So similarly here also it will follow the same. So as per Thevenin theorem, what we have is, as you can see here, this dotted region contains a network. So it can be any network, any complex network, but it should be obviously linear and bilateral. So this network can be converted into this simpler network containing a voltage source and the series resistance. As you can see, the load that we are calculating across RL will remain same, and the whole remaining circuit will be converted into this simpler network. So as per the theorem, any two terminals of a network can be replaced by an equivalent voltage source and an equivalent series resistance. Now how do we calculate this voltage source and series resistance? This voltage source is calculated across the two terminal of the load when the load is removed, or we can also call it as it is the open circuit voltage across the load terminal. Okay, and the resistance is the open circuit resistance from the load terminal when the remaining sources are replaced by the internal resistances. So for determining RTH, it is nothing but equivalent resistance of the circuit measuring from the terminal where we have the load, and all the independent sources will be replaced by their internal resistance. That means, as we have discussed in case of superposition theorem, for voltage source, ideal voltage source, it will be short circuit. For ideal current source, it will be open circuit. Okay, so after obtaining the value of VTH and RTH, we will determine the current IL using this simple network. So this is about Thevenin theorem. Okay, so now let us consider a example. So how to solve it? So this is one example containing three sources and resistances. All are independent sources, so there is no case of dependent source here. So let us see how we can solve this circuit using Thevenin theorem. So let us consider first redrawing the circuit. So first let us consider for VTH. So for VTH, what we have to do, we have to remove the load terminal and determine the voltage across the terminal. So that means we have to calculate VTH here in this terminal. Okay, so in order to determine VTH, first we have to determine the current in these two loops. So suppose they are I1 and I2, and since this terminal is open circuited, so there will not be any current flowing through this terminal or flowing in this loop. Okay, so to determine I1 and I2, as you can see, this forms a super mesh, as we have a current source in between two meshes and there are no other current source in the outer loop. So we have to apply super mesh procedure here. So in order to start with, the current in this we have is, this is I1, this is I2, this is 13 ampere. So as per KCL, we have, by applying KCL at, suppose this is node 1, so we can apply either here or on the other terminal. So applying on node 1, we will have I2 minus I1 equals to 13. Then writing KVL at super node, we have 150 minus 15 I1 minus 60 I2 minus 40 I2 equals to 0. As we know, we always write down KVL of super mesh. Sorry, this should be super mesh at the outer loop, right? So at the outer loop, this is our equation of KVL. Now after solving these two equations, number 1 and number 2, we'll have the value of I1 and I2. So I1 will come out as minus of 10 ampere. So in order to save time, I am not doing the calculations here. So you please try the calculations and you will find the value of I1 and I2 as minus 10 and 3 ampere. Okay. So now how to determine VTH? For determining VTH, we can write down an equation in the outer loop which will contain VTH in the loop itself, and then we can determine the value. So if we can do it that way, or other way around, we can also write down an equation in this loop which will contain VTH as a part of the loop. Okay, so let us consider the third loop. So it will be 40 I2 minus, in this direction VTH is negative, then minus 50 equals to 0. So from here we will get the value of VTH and it will come out to be 70 volt. Okay, so we have solved for VTH. Now let us see what will be the value of RTH. So for RTH, again we have to draw the circuit. So this is our circuit again. Now what we have to do? We have to determine the value of RTH from the load terminal, or calculate the value of RTH from the load terminal and remove the supplies and replace it by their internal resistances. So this is current source, these two are voltage source. So we have two short circuits and one open circuit. That means this will be short circuit since we have voltage source, and this should be open circuit, and this is our RTH. Okay, so this is the circuit for RTH. So we have to calculate now. So these two are in series in parallel with this. So RTH is 15 plus 60 whole parallel to 40. Okay, so this will come out to be 26.09 after calculation. So now we can determine the Thevenin circuit. So as per Thevenin theorem, this should be VTH, this should be RTH, this should be RL. So we have the values. VTH is 70 volt, RTH is 26.09 ohm, and RL is 30 ohm. So we can apply a simple KVL equation here and determine the value of IL. So IL value will be equals to voltage divided by the resistances. So 26.09 plus 30, both are in ohm range. So this will be equals to 1.25 ampere. Okay, so this is the solution for current IL. So let us see whether the same circuit or the actual circuit, that is our first circuit, will give the same value of current or not. Okay, so instead of doing the solution, we can take help of simulations here. So let us do the simulation and see what will be the output. Okay, so after making the circuit in simulation, so as you can see, we have all the components prepared. That is roughly 150 volt, 15 ohm, 60 ohm, 30 ohm, 50 volt, 40 ohm and 13 ohm. So our answer was 1.25 ampere that we have obtained after applying Thevenin theorem. So let's see what is the answer by applying it to the whole circuit. So answer is coming as, this is the current, so it is 1.248, which is nothing but 1.25 ampere. So we have seen that Thevenin theorem is verified. So whatever current is produced across this 30 ohm resistance will be similar as the current produced in the Thevenin circuit. Okay, so this is the Thevenin theorem. So using Thevenin theorem, we can convert any complex circuit into a simpler network containing a voltage source and a series resistance, and then our equations and solutions becomes easier. Okay, so following this, we have another theorem which is known as Norton theorem, which is almost similar to the Thevenin theorem, and you can say that we already know source conversion, how we convert a source conversion from voltage to current. We draw a voltage source and a series resistance, and that is converted into a current source and a parallel resistance. So that using that logic, we can say it is similar to Thevenin theorem. That means the Norton theorem is given by, see, as we have as we have a linear network and a bilateral network, it should be linear and bilateral, similar to Thevenin theorem, and any complex network can be converted into a simpler network. Now each contain a current source and the parallel resistance. Okay, that is the only difference between Thevenin and Norton theorem. That is also in Thevenin theorem is also a simpler network. In Norton theorem also it is a simpler network. So the changes is, in Norton theorem you have current source and a parallel resistance. So remaining equations, or how we determine the this current source and the equivalent resistance, is for determining this current source is known as ISC, stands for short circuit current. So what we do, we remove the load and then replace it by a short circuit and determine the current. So whatever be the current, that will be the value of ISC. Then next, for determining RL, which is similar to RTH, that is, we have to open circuit the load and then determine the equivalent resistance, calculating or measuring from the side where we are open circuiting the load and replacing the independent sources by their internal resistances. So by doing it, we obtain the value of RL similar to RTH, and then we put it in the Norton circuit, which is ISC and IRN, and then determine the amount of current. Which this so this IL is equals to the IL that is produced here in the original circuit, or as you can say, this is our original circuit, this is our Norton circuit. So the IL that we can get here is similar to the IL that we are getting here. Okay, so now let's see how to solve this circuit using Norton theorem. So as we have discussed, for Norton theorem we should have short circuit across load resistance. Okay, here we have to determine the current across this 10 ohm resistor. So first let us duplicate the circuit. So for calculating ISC, so we have to remove this and put a short circuit here, and then determine the current that is flowing through this branch. Okay, so now we have this circuit. So in this circuit, if we write down loop currents, then it will be 3 currents, I1, I2, I3. So applying it into the first loop, so in loop 1, applying KVL in loop 1, what we have is 2 minus I1 equals to 0. So the value of I1 is 2. Then in the second loop, you can observe that this is a super mesh containing a current source in between 2 mesh. So we have to write down KCL and KVL both. So KCL in super mesh, so we can consider this point. So here we have I2 is moving in, I3 is moving out, and 4 ampere is moving in. So the equation will be I3 minus I2 equals to 4. Now applying KVL in super mesh, we have minus 5i2. That means we are applying in the outer loop. So minus outer loop means this. So minus 5i2, then minus 15i3, and there are no other components equals to 0. So from here, so from these two equations, we'll have the value of I2 and I3, two equation 2 unknown. So I1 we have obtained 2 ampere. So after solving, I2 will be minus 3 ampere and I3 will be 1 ampere. So what is ISC? ISC is I1 minus I2. So it will come out to be 2 minus 3. So it is 5 ampere. So we obtain the value of ISC. Now let us determine the value of Rn. So for determining the value of Rn, we will again consider the circuit and determine the equivalent resistance. So now what we have to do? We have to determine the equivalent resistance here across this terminal and remove the independent sources. We have two independent sources. So this is a voltage source, so it will be replaced by short circuit. This is a current source, so it will be replaced by open circuit. And here we have to determine, it should be Rn. So what is the value? As we can see, this is removed. These two are in series in parallel with this. So that means Rn is 5 plus 15 parallel to 1 ohm. So this will come out to be 0.95 ohm. So now let us draw the Norton circuit. So this is a Norton circuit. We have 5 ampere here, we have 0.95 ohm and our load resistance. So the value of IL will be, so we can write down here CDR, using CDR we can determine the value. So it will be 0.95 divided by 0.95 plus 10 multiplied by 5 ampere. So after calculating we will get it as 0.43 ampere. So this is the answer. So let us check by doing simulation what will be the answer if we apply it to the original circuit. That means if we apply it here, whether we are getting it 0.43 ampere or not. Okay, so after preparing the circuit in simulation software, so we have here 2 volt, we have 1 ohm, we have 10 ohm, we have 5 ohm, this is 4 ampere, this is 15 ohm. So after simulating the circuit, we are getting the current across 10 ohm to be 434 milliampere, so which is nothing but 0.43 ampere. So the current is same. So we have also proved Norton theorem. So what we have learned, that any circuit can be converted into a simpler network. There are two types of network. One is Thevenin network, second one is Norton network. So in Thevenin network, the simpler network will be a voltage source and a series resistance, and in Norton network it will be a current source and a parallel resistance. So we can convert any complex circuit into a simpler network like this and then solve our numericals. So I hope you have understood what is Thevenin and Norton and how we can minimize the circuits using them and do our calculations. So thank you for joining. So in next class we will be discussing how or what will be the changes occurring for using Norton and Thevenin theorem when we have dependent sources. So yes, it will be slightly different because we cannot remove the dependent sources, so we will be having difficulty in determining the value of RTH or RN, because for determining the equivalent resistance we should have we should not have any sources in our circuit, right? But we cannot eliminate the dependent sources. So what will happen there, we'll see in the next class. Thank you.